Hello, everyone. Nice to have you all here. My name is Benedict, and I am the co-lead for the computer vision group. I am assisted by Amit Taylor, who unfortunately cannot be here with us today. He had a couple of engagements that came up, but we are in good hands. We have Patrick here to present to us today. Patrick is a PhD candidate at UC Berkeley at the moment, and he is being supervised by Professor Darrell and Professor Gonzalez during his PhD program. So I would like us to just welcome Patrick as he joins us today and gives us a bit of a peek into his paper, which was released a while ago on visual question answering. So thank you very much, Patrick, for being here today, and I turn the tables over to you. Yeah.
Yeah, thank you very much for having me. And
Yeah, sure.
I'll share the screen. Can you guys see the screen now? Can you guys see the screen?
Yes.
Yes,
Okay.
we can.
So I think I just get started. And today I'll talk about my previous work on the multi-image reasoning called Visual Haystack. I changed the title a little bit because we just do a major update a few days ago. So Visual Haystack is a visual-centric needle in haystack benchmark. So I'm Patrick, and here are my great teammates at UC Berkeley. So today I'm very happy to have a talk at Cohere for AI. So yeah, thanks for having a quick introduction. So yeah, I also have an introduction slide. So I'm Patrick, and I'm a cat lover. So as you can see the image, and I'm
Hey,
currently
Patrick,
doing a PhD. What?
we
Patrick,
cannot see
we
your
can't see
slide.
your slides.
Yeah.
Oh, really?
Yeah.
Let me see. How should I do? Um, Dismiss. Why I'm not able to share my screen? Oh, entire window. Okay. What about this one?
Yes. Yes,
It
we
works?
can now. Yes, it works. It works.
Okay.
Yeah.
Yeah. So I just redo it again. I'm Patrick, and here are a lot of teammates at UC Berkeley, and we're happy to present our recent works on Visual Haystack, which is a vision-centric needle in the haystack benchmark. So thanks for giving me a quick introduction. So I also have a quick introduction slide. So I'm Patrick, and as you can see the image, I'm a cat lover, and I'm currently doing a PhD at UC Berkeley, and I'm from Taiwan. So yeah, I focus a lot research on large multimodals, working with Trevor Darrow and Professor Joseph Gonzalez. So let's dive into the topic we're going to talk about today. So I think many visual problems in real world requires long context reasoning. For example, like long context visual question answering is the most interesting or promising applications nowadays. For example, I'm personally a cat lover, so I also have the problem that I want to find a specific image containing a specific context and with my iPhone. So we probably want to answer the question about the photo albums and collections, but hopefully Gemini's recent X photo features can probably solve the problem. And also there are a lot of applications like analyzing patterns in medical imaging or climate change from satellite images or surveillance footage, just a list of few of them. So anyway, I think nobody will uh, reject or will say that large-scale visual question answering is not important in the future. So just a background, uh, probably in 2024, there are a lot of long context, large multi-models, or somebody will call it vision language models, are coming out. So basically, the architecture would look something like this one. We have an input image, and we use some visual encoder like clip to extract the feature of the image, and then map that to the space of large language model and put that to the language model to do the next token prediction. For example, like for this image, maybe the first word would be horse, and then could be a horse is in an image and a person is riding that, something like that. So for the long context, large multimodals, the only difference is that they enlarge the context window from, for example, 2K or 32K to, for example, like GPT-4o have 128K and Gemini 1.5 at 2 million context length. So it's way larger compared to what it was be maybe 1 year or 2 years ago. But we want to ask the question in this work, does taking more visual tokens lead to improved results in large-scale multi-image QA? Specifically, taking more images sometimes doesn't indicate that the performance can actually do well on multi-image question answering. So we need a benchmark, and that is the motivation of the work. And I'm not sure if somebody have heard of needle in a haystack benchmark, but anyway, I'll introduce a little bit again. So this is a common benchmark to evaluate long context model in retrieval and reasoning, specifically for large language model and large multimodal models. So the original needle in a haystack benchmark is presented in a YouTube link here. And basically what the original author did is like they inserted random information. Like the best thing to do in San Francisco is go to somewhere and do something. And then insert that to a random position in a very long context, for example, a guy's essays, and then feed all these information to like GPT-4o and ask what is the best thing to do in San Francisco. So if the model can actually reason long context models, I mean, they can retrieve and reason in context, they should be able to answer this question. I mean, even though it's a very tiny information in the large collection of the inputs, they still should be able to answer it if they claim that their model is a long context model, right? So basically, this is the idea of needle in a haystack benchmark. We inserted random information or a tiny information we call needle in a collection of the data. We call it haystack and test if the model can correctly retrieve the information and answer the question. Oh, by the way, this is the actual benchmark that we are currently using to evaluate large language model, but not for the vision. So we can do the same thing for the vision. For example, we insert a certain object or certain image with some key features into the image and test if the model can retrieve and answer that. So far, so good. It's a background project, background of the work. Okay, I think I just keep proceed. So let's dive into the Visual in the Haystack project. So previously, there's a benchmark, Gemini, in their tech report, they present the first vision-centric or the first vision needle in a haystack benchmark. So what they did is just like they replicate the text needle in a haystack challenge. They also add the random information in a collection of images. So what they did is like they overlay the transcript on a certain frame in a very long, for example, 2-hour video. And then they just feed the 2-hour video to the model and ask Gemini 1.5, what is a secret word? And the Gemini 1.5 successfully found the frame and answered that the secret word is the needle word, something like that. And in their tech report, they just claim that, okay, our Gemini 1.5 is able to understand 2-hour or long context video or visual information. But if you think about it, it's probably not that true because in reality, we probably just don't want to, for example, this image is outlier. And also, it is some OCR-centric challenge. Is not similar to what we are interested in real world. So instead, we propose a new benchmark called Visual Haystack, which we replace the text needle to a visual needle. Specifically, we collect a large haystack and we make sure that there is only one, for example, one image with a truck and the rest of them didn't have them. So we always ask the question like, for the image with the truck, is there a dog? It seems like a very easy question for the model. But as you can see that in the previous Gemini style challenge, their performance is always 1.0, as they claim in their paper that our model can actually do pretty well or reason long context information. But if you replace their challenge to the visual haystack datasets, you can see that the performance degrade a lot for either GPT-4o and Gemini. So yeah, visual haystack is the first, I think it's the first truly vision-centric and also realistic needle and haystack benchmark that challenge uh, open source or proprietary large multi-models. So it's the motivation for us to design a new benchmark and first to evaluate all of them and then trying to do better on top of existing development in nowadays. So here are some visualization of our data sets. It's quite easy. The single needle track is something like this one. For the image with the laptop, is there a couch? So some of the images there contains the couch, but the model needs to first retrieve the image with the laptop and then answer the question. So the answer is no. I think for we humans, this question is pretty easy. We can see 10 images and easily find out that, okay, there's only one image with the laptop. And the question, the answer should be no. And for multi-image needle track, it's also very easy. So we always ask the question like, for all images with something, do any or all of them have some target objects? And it's also very easy. We first need to use the information in Apple to locate some images, the needle images, and then figure out that, okay, none of them have a dog. So the answer is no. So visual haystack dataset should be easy, right? So it is our first thought. But after a deep dive, we just found that the model actually cannot do well on a very easy task. And it is not a comprehensive task for large multi-models, but at least we believe it's a great unit test or foundation benchmark that every large multi-models should be able to pass if they claim that they can reason long context information. So far, so good. We're diving into the evaluation of existing large multi-models. Okay, I just keep going. So
Yeah, please.
yeah, so we just want to ask the questions. For this very easy benchmark, can current large multi-models or open source or even proprietary ones handle these long context visual inputs? It should be very easy. You see the questions. The question is so easy. And the images are all in domains. Actually, all the images are from Cocoa datasets. There's no excuse that the model cannot do well on Cocoa because I think they are probably part of their training sets. Yeah, so we just do an evaluation. And first, we found that the models are susceptible to visual distractors. So in the single needle challenge, we first draw two lines using a detector oracle and a caption aggregation. So the first baseline is just like, okay, we assume or we just use Google's OWV2 detector as an oracle. And we always, in this oracle baseline, we just know that what objects we're interested in. So we just use a detector to detect the target objects and the needle objects, and then do a very easy logic way to answer the questions. So you can see the performance just gradually decay, but it's actually very smooth from one image to 10K images. But for the caption aggregation baselines, which we first use the large multi-model models to caption the image, and then use the language model to aggregate all the information. Because the captions sometimes didn't capture what the question is, so the performance can, yeah, it is obvious that the performance is way lower compared to the Oracle baseline and also probably some visual question answering baselines. So we just plot a bunch of large multi-model models on that, like GPT-4o, Gemini, Plan 2, Intern V2, and Microsoft Phi 3, and also, yeah, Mplot. So as you can see that, first of all, none of existing large multimodals can take more than 100 images. Actually, the GPT-4o and Gemini 1.5 Pro, although they claim that they have longer context length, they actually reject our API request because they say exceed our API payloads. And existing one, for example, like Qwen2, Intern VO2, they exceed their context length. And also for 5.3, they cannot fit in 4 A100 GPUs. So it's still not feasible in real world challenge. So anyway, none of existing models can take more than 100 images. And also, you can see a huge performance drop from one image to, for example, like 50 or 100 images. And specifically for one image, you can see that the single image visual question answering performance is quite good, or at least over 80% is quite close to the Oracle baseline. But as the number of images grows, the model seems to mm, didn't do well on handling such large information. So we guess the models are susceptible to visual distractors because uh, there's only one image that related to the questions. But if we keep insert some irrelevant images, the model just being confused and cannot answer well. So the next one. So the second finding is that we found none of existing models can do well on cross-image reasoning. So previously, we just mentioned that in the Visual Haystack benchmark, we have single and the multi-needle track. In the multi-needle track, we require the model to reason the question like, do any of them or do none of them, do all of them contain some specific image? So it requires the model to do at least reason more than two images and aggregate the information. So as we can see, if we ask the same questions to the model with either one image, two or three images um, related to the questions, and in this case, because it's an Oracle challenge, we didn't add any irrelevant images to the model. So the number of images to the models is always one, two, and three. But you can see that if we increase the number of images from one to two and requires the model to integrate their information together to answer the questions, there's a huge performance drop when we do cross-image reasoning. But if they are doing from two to three, you can see it stabilized or even gradually decrease. So we hypothesize that the models have difficulty in cross-image reasoning. So if we combine the two, I mean, also added the visual distractors to the multi-needle challenge, so it becomes our original design of multi-needle challenge, the performance even degrade further compared to the single image result we showed earlier. One interesting thing I want to show is that you can see for GPT-4o, this one, if we didn't add any visual distractors, their performance can be better compared to Gemini. But if we add a lot of visual distractors into it, their performance can be worse compared to Gemini by a large margin. So yeah, and also you can see in single image, it's the same situation where the GPT-4o consistently perform worse compared to Gemini when there are some distracted images.
What are the kind of visual distractors that you use here?
Oh, yeah, that's a good question. Actually, in our visual distractor, we just add a lot of random images. We only make sure that there is no needle objects we're interested in to make sure
Okay.
that our data set is correct. But it's a good
Mhm.
question because a lot of people just suggest that I can do some hard negative, like for example, if I add a couch, maybe I can add a chair, I can add a sofa or something like that to challenge the model. But actually, we didn't do that. We just
Okay.
randomly add a lot of things to that.
Okay. So that kind of like generalizes, or your model is able to detect on like kind of like not see them and focus on the the attention kind of like focuses on the images that are important, right?
Yeah.
Mhm.
So I think they probably have a huge room of improvement on how to enable the model to focus on something that truly important or relevant to our questions, right? That is our hope.
Cool.
Yeah, so they also have problems on retrieval and reasoning for a certain context. And as you can see, for open source models like Qwen2, Intern V2, their performance is only 60, 55, or 50. Oh, by the way, because the question is only asking the model to do yes or no, so the random guess performance is 50%. And we make sure that our dataset is not biased by first making sure that the number of yes and no in the dataset is has the same number. And also we use a blind baseline, which means we use the Llama 3 models, 3.1 models, and ask them the questions without providing the image information. And their performance is quite close to 50%. So which means in order to perform well on our benchmark, the model needs to read or at least understand the visual context to answer that. So I think lower than 60% is not good because the baseline is 50%. I mean the random guess. And the final finding, I think, is the most interesting one, is the positional bias. What does it mean? So we plot this 2D plots. If you guys are familiar with the needle in haystack benchmark, they guys also plot something like that. So I'll elaborate a little bit further. So the x-axis is the number of haystack. So as we showed earlier, our haystack size can be, for example, like 5, 10, 20, 50. So that is the input to the model can be from 1 image to 100 images. And in the single needle track, there's only 1 image correlate to our questions. So we can put that image at the beginning of a lot of images, or at the end, or somewhere in the middle, right? So we just ablate the position of that key information as the y-axis. So as you can see, if there are only 1 image in the model, so we only need to consider 1 cases because there's only 1 possibility to put that. But if there are 2 images, there are 2 positions we can place, and so on and so forth for 3, 5, 10. So as for Gemini 1.5 Pro, we can see that from 1 image to 100 images, the models perform much better if that key image is at the beginning, but they perform gradually worse if the images is put somewhere at the end of the context. But for GPT-4o, we just found they have a tendency to focus more on the beginning and on the last. And for this one, the Qwen2 VL is the open source models, and it seems like at the beginning they tend to focus on the last image, but more than 10 images, they tend to focus on at the beginnings. We've hypothesized that it's because the model is trained on specific data, and that data have some inductive bias, or I don't know, some other bias. So the model also show this tendency. So we can break it down or take a closer look from that 2D plot. I mean, I break it down to 1D plot. So it is Gemini. Here's 1 image, 2, 3, 5, 10, 20, 50, 100. And it is clearly that the models have some tendency to focus more on the first images. Although there are some error bars, and it might be always consistent like this one or this one, but I think overall they focus more on the first images. And for the the GPT-4o model, they tend to focus more or less somewhere in the middle. So if you are familiar with the NLP domain, there's a very famous paper last year called Lost in the Middle. That is a paper they found in NLP domain where the GPT-4o, or at that time it's probably GPT 3.5, cannot focus well if we put a lot of documents and somewhere key information is at the between of the context. So yeah, we also, I think it's the first work we found that GPT-4o also have lost in the middle situation. Yeah. Is there any questions so far?
Are there any questions, please?
Uh-huh.
I don't think there are questions. I think we can move on. Perfect.
So I just keep moving forward.
Yeah, just continue. Thank you. Yeah, no
Okay.
questions right now.
Okay. So yeah, given this observation, we just asked the question, can we do better at large-scale image, multi-image QA? That is the key questions we want to ask at the beginning of the project, after we evaluate a bunch of a bunch of existing solutions. So we present a new method called Mirage, and which stands for multi-image retrieval augmented generation. So I think it's the first visual RAG framework with chaining with the large multimodal models that can retrieve and reason across multiple images. And it's probably the first work that can scale to actually tens of thousands of images. Because as we showed earlier, none of existing solutions can scale to more than 100 images and also perform well. So it's our architecture. We propose a new architecture and also some data sets to support us, and we'll elaborate that in the later slides. So first, our model is quite easy. We have a lot of images, and for each image, we encode that using a clip as the same as Lava model. And the only difference is that we are trying to compress the visual tokens from, for example, 576 tokens to 32. Because if we can compress the number of tokens more, we can fit more images in our language model, our downstream language model. Yeah, so actually we just use a compressor, and in a sense, it's a Q-former cross-attention architecture with learnable tokens to compress that to 32 tokens. So which means our model can take 18 times more images compared to our baseline open source model called Lava. And the second stage is the retriever stage. So we want to drop irrelevant images to the model. So until now, we process every image individually. And for each image, we will the retriever will take both the questions and this compressed embedding altogether and predict whether the images are relevant to our questions or not. And if not, we will dynamically drop that image. Yeah, so it's very easy. The retriever is just a stack of transformer layers, and they take these as their context and predict either 1 or 0 and train with binary cross entropy. Pretty easy. And the final one is the large multimodals. So after we pass all of them, we need to answer the questions, and to support the whole training, we need to have a data set, because nowadays we only see a lot of single image question answering data sets. And this time we just create the first vision language model fine-tuning data set for multi-image, and it's a 1.2 million training set with the augmented Lava dataset and also a bunch of real-world multi-image QA datasets with red QA, and this one is the QA from Wikipedia, and this one is the QA questions from a bunch of slides. But as you can see, that the data is quite limited, because there's still a long way for us to explore in the multi-image QA domain. And here are some results. First, we revisit the single needle track, and the red line is our model called Mirage, and it's only 8.3 billion models. And as you can see that on single image cases, our model is competitive with all the open source alternatives. And also, as the number of images grows, our model just gradually outperforms even GPT-4o and even Gemini after 50 images, and consistently, grows much better on 100 images. And it's also the only work or only solution that can scale to literally tens of thousands of images. So yeah, that's the takeaway. Like the Mirage can scale to a lot of images, outperform GPT-4o, Gemini 1.5 Pro when taking 50 plus images. And for multimedia track, this is our result. As you can see that there's still room of improvement on both data and model design, because we hypothesize that the current multi-image QA dataset is quite restricted, or the data set is not that diverse compared to the single image one. So in the previous track, we can always, because the question is always about single image QA, so they can do quite well because your data set is quite comprehensive and they cover a wide range of cases. But for multi-image cases, I don't think the model do pretty well because theoretically they can do better. And yeah, we have a lot of things to do in the future, but still our model in most cases is the best open source model and can scale to more than 100 images, of course. So for the conventional VQA task, we benchmark the model Mirage with a lot of existing methods, either multi-image QA and single image QA. And as you can see that our models perform significantly better the multi-image QA task compared to prior solutions. And also on single image QA task, we show competitive performance with others baselines. So I think here are some takeaways. First, in this work, we introduce a vision-centric and realistic long context benchmark to large multimodal models. We call it Visual Haystack, and it's much better than existing ones, which is the OCR-centric or the text-based, and also the artificial ones. And second, the current vision language model are prone to visual distractors, which means if we add a lot of irrelevant random images, the model just cannot focus on what truly matters. And if the questions requires the model to integrate image information from multiple images, the model just do worse on that, and also exhibit the positional bias. And third one, after we do a lot of observation, we present Mirage, which is a pioneering visual rack framework that can take tens of thousands of images and mitigate some of the challenges like visual distractors. And because we have the retriever, we probably no longer need to care about something like loss in the middle or some positional bias issue because we can filter out irrelevant image at the first place. And finally, as you can see in the results section, the Mirage and Visual Haystack is definitely not the endpoint, but a starting point of multi-image QA community and encourage people to investigate more or study the long context large multimodals. So yeah, that's all. And it's our project page. And thanks for listening. If you have any questions, please ask me. I know it's a little bit earlier, so we probably have more time to do QA, or I can explain more on specific topics if you're interested.
Thank you very much for the presentation, Patrick. It was very nice. Sorry if the
Thanks.
place is a bit dark here. My power is out right
Okay.
now. So, yeah. So I just wanted to know is today's presentation was actually quite short. It was very fast.
Okay, I can elaborate.
Yeah,
Yeah.
no, that's not a problem. It's not a problem. It's just something quite interesting to note. Yeah. So let's see if there are any questions. Okay, so Andrew wants to have some idea as to how the mathematical reasoning works for the project that you did. Can you elucidate a bit for Andrew? He wants to understand the mathematical reasoning behind the paper, behind the work. Yeah.
Sorry, I can't.
Yeah.
Mathematical reasoning works.
Yeah.
Oh, you mean the mathematical reasoning for all existing models because you currently you see a lot of models can do well math tasks. Is that what you're asking?
Andrew, if you're here, could you please if it's possible, could you unmute and elaborate a bit, please?
Okay, hello, can you hear me?
Yes, yes, we can hear you. Patrick, can you hear him?
Yes, yes.
Okay.
So I mean,
Yeah,
are you asking the question like why the model can answer some, for example, U.S. University enrollment questions or something like that regarding math or?
so earlier I posted a question in the chat that can the model answer like math question that is in the form of an image. So if I have a picture with maybe x squared plus 4x plus 5 is equal to 0, and the model produce like maybe the real numbers or something, like answer that question. And someone commented this. So I just want to know how it's able to do this.
Sorry, a little bit noisy or unclear. Can you repeat the question again? Sorry.
Okay, so if I have an image of a math question,
Uh-huh.
let's say I have a question paper and I take a picture of that question paper and I
Yes.
feed the image into the model and the model answer that math question. And if it can, how does it go about
Okay.
doing that?
I think for contemporary model like GPT-4o, Gemini, or some current open source solution like Qwen 2 interns or even Microsoft Phi models, uh, the reason why they can do well is the data. There is no secret behind the deep learning model. They are all because we feed the model with a lot of uh, relevant data in their training sets. So yeah, because what they did is essentially the same. They didn't do anything uh, very surprising or very complicated. They just feed the image to the model, and then the model will, yeah, the same, use the clip to extract the features and then align that to the language space and then do the QA. So I think the only thing that matters is because we feed the model with a lot of math questions, just like we human. We don't know what happened in our brain, but they just can reason that because we do a lot of homework.
Um, Andrew, does that answer your question? So basically, what Patrick is simply saying is the model right now, the specific model for this paper, cannot answer math questions because it's not trained on math data. Basically, it's about the data.
Sorry, I mean,
Does that make sense?
the model. I mean, they can somewhat answer that question because I think increasingly
Oh,
people
okay.
is more interested in this kind of capability. Like, can a model do well on Olympic mathematical tasks, or can it do well on Olympic physical tasks? And then they just keep feeding that kind of data to the model.
Okay, yeah,
Yeah,
makes
yeah, yeah.
sense.
So my question, my conclusion is that the only secret is data. If we can have a lot of data, the model can generalize well on the whole domain. They can definitely answer that question.
Yeah. So Andrew, does that answer your question?
Yes, thank you.
Okay, nice, nice. So okay, Fed says that it depends on the performance of clip, which makes some sense because if you are encoding a math question as if you're encoding a math question as an image, then it makes sense that the image has to be encoded well by clip. Yeah, so it makes some sense. Fed's opinion here makes a bit of sense. Then
Yeah.
Mishra has a question. He wants to know what makes Mirage better than other models. And then he also wants to know if the clip encoder functions. He also wants to know if it is the clip encoder or the retriever that makes the Mirage model better.
Okay. So both are very great question. First of all, I don't think we do anything better compared to existing one because I mean, we also use the clip model to do that. And the reason why we can perform better than existing models, I mean, on conventional VQA test, for the single image QA, we didn't actually do much better compared to existing one. For example, like GPT-4o and Gemini, they also do quite their performance is actually better on, for example, like text QA questions because I think they have some OCR capabilities behind their backend. And I think the only reason our model do better is that we have a retriever, so we can exclude a lot of irrelevant information at the first place. So this brings us to our second questions about how good is our retriever. So in our paper, we show that our retriever's performance is can be much better compared to clip. So if there are, I remember if there are only 10 images or 20, our retriever's performance can be higher than 50 or 60 on top one retriever accuracy. I mean, if there are 2 or 3 images, they can be 90 or 95. And for 10 images, probably 70 or something. But it's still a long way to go. And as you can see that this retriever performance can be definitely be enhanced. But with this very naive design, we can at least beat a lot of existing existing methods, which means the retriever is probably the must to handle the very large scale QA. Does that
Okay,
answer your
nice.
questions?
Yeah, I think
Different.
that answers my question. Thank you.
Yeah, nice.
Yeah.
Nice. And Afed had a question. It was like, how good can Mirage be at retrieving the relevant image? And I think it's quite good, but I'll let Patrick answer that question.
Okay, so I think what you're trying to ask is like if we only feed the relevant images to Mirage, right? And how good it is.
Yeah,
I don't think
Well,
that. Okay.
if I may add, like it was a really long sentence, and I broke it down to 2 parts. And I was actually answering the question about the mathematical performance of the Mirage on the math dataset or something. So I wrote it on 2 sentences, and I said, hey, well, this depends on the performance of clip mostly, and how good it can retrieve the relevant image. So
Okay.
it's not actually a question in here.
Okay. Okay.
Oh, so
I
there
thought
are
it
actually
was.
2 questions. Okay. So yeah, I think I just answered the question about the retriever. Like our retriever performance as common images is only not only for 2 images it's about 90, 95. 3 is also the same, but for 10 it's probably degrade to I don't know 80 or 70. But they consistently outperforms the clip models in our paper. And but yeah, as suggested, I think it's a great observation that we can do much better. What is that? Math questions. If I mean, clip can do well on some semantic matching between the image content and a text, but there are a lot of semantic matching rather than, for example, like math questions, which requires the model to have a very deep understanding on the text itself. So an easy solution for that is add another visual encoder, which is probably the Microsoft's layout LM, or we just add the OCR head here and directly concatenate that information in the input tokens. I think that is a common practice in some contemporary other solutions nowadays are trying to do.
So cool.
Okay.
I had a quick question.
Go on.
Yeah. So this was a query regarding the clip. So have you tried on different sets, like the encoder part, like using the siglip, or like
Oh yeah,
metaclip, for example? Yeah.
Yeah. That's a very great question. So I do try the metaclip, but that is a very a little bit nuanced here because okay, now the clip feature is actually not the image-based feature. So in a lot of previous practice, we will take the last 2 layers. I mean, the features 2 layers before the final image features as the image feature because that features contain the the region information more, and we just feed the patch information into the alignment layers, and then feed into the language model tokens. So in the metaclip, their default image resolution is 224 by 224, and in what clip I'm currently using is 336 by 336. And we've just found that the image resolution actually matters. If the clip encoder can take the image. I mean, if they are trained with larger input, their performance can be much better. So yeah, C-clip can be a better one because theoretically their image resolution is higher. But yeah, that's a great extension to probably 1 or 2% improvements group performance improvement. But MetaClip, I do try it, but unfortunately it didn't do well.
Oh, okay.
Yeah, but it's a great question. I mean, they didn't do well. It's probably not because they're bad, but probably just because there are um, a lot of options I need to try. For example, if I need to try the last layer or last two layers or somewhat layers. Yeah, but the one thing I can tell you is that the image resolution matters, and MetaClip have the resolution of MetaClip is smaller. So I hypothesize that okay, it's probably the reason. I just give up and stick back to the original clip that everybody's using, and I can everybody show successful results.
Did you also try open clip here?
I think open clip. I think I'm using open clip or something. Clip 336 by 336. I just use this one.
Okay, yeah. This
Yeah.
Yeah.
Because everybody just shows successful results on that VQA test. So I just first try this one. Okay.
Okay. So with Mayank, do you have any further questions or you're satisfied with the state of things?
No, I was just referring to the fact that open clip is a bit different. I will paste it in the chat.
Okay.
Yeah.
Okay. Thank you very much for your contribution to the discussion. Yeah.
Okay. I have one last question. Like when you're using clip to retrieve the images, you're just retrieving only the most similar one, or like top 5, or
yeah, that's a great question. So with a retriever, in a single image track, we always pick the top one, but for multi-image track, we pick top 3. Yeah, that is just a hyperparameter we can tune. And actually, we can also use a larger way to tune the model, like if their output score is higher than 0.5 or 0.6, something like that, and you just pick it.
okay.
Yeah, but in practice, in our experiments, we take top 1 for single needle, top 3 for multi-needle, and also top 3 for all the multi-needle image question, because as you can see that none of the existing data set contains the relevant images more than 3, but they do have more images as input.
Really nice work. It's really, really impressive how you figured this out. This sort of like reminds me of RAG, but for images, and really nice work.
Yeah, it is essentially a RAG variant.
Yeah.
It's essentially a RAG variant.
The motivation of the work is that at the beginning we just found that okay, GPT-4o didn't perform well on multi-image QA, so we just say that it's probably because we need a RAG. And we just first developed something, the Mirage is developed first, and we need a compressor because at that time we don't have Llama 3.18 billion. It's only 2K models like Vicuña or Llama 2, and then we just suffer from it. So we need a compressor, we do need a retriever. And after that, we just found out, okay, we now need a benchmark to evaluate existing models. And then we just develop a very easy benchmark called Visual Haystacks after we found the Gemini's tech report, and we found that none of the existing models do well. So this motivated us to do a lot of findings, like we found the models are prone to visual distractors, difficult in cross-image reasoning, and have some very interesting lost in the middle or out of bias. So we just stack all the things together and make it work. But yeah, it's definitely not the endpoint, it's the starting point. As you can see that, okay, the model, you can see the data set only contains 1 to 3 images. Is that actually a real world problem? Something like that? We still have a long way to go.
Yeah.
Yeah.
So it might just be the starting point, but it's quite a very good starting point, a good launch
Yeah.
point. Yeah. So thank you very much for your contribution, Alfred. Yeah. So we have one more question from
Okay.
Jan Juice. Yeah. So is Jan Juice still on the call? Would you like me to read out your question, or you would like to ask yourself live?
No, I'd be happy to ask myself. Thank you, Benedict.
Okay.
Patrick,
Yeah,
first
nice.
of all, thank you for a fantastic presentation. It triggers a lot of things that I've worked on in the past. So that's the reasoning behind my question. Could this system potentially be used for re-identification, for example, of persons or of certain objects across, could be a car, for example, across multiple camera feeds that have gaps in their fields of view, allowing for a reconstruction of the path through time and space, for example, through a generated video? Could your system be used for that?
I think the question can break down to two parts. One is that this systems can be definitely used for reality because we have multiple cameras on different views. So it's the same questions of answering questions for a set of images. It's the first question. Yes, it is some reasonable downstream applications. And go back to our second question is that after you do some reasoning of that, you want to reconstruct, for example, a specific person's footprints from one location to another, and so you need some reconstruction, right? And
yes,
for now, the model data cannot output any visual tokens because they only do text QA. But you can definitely train the model to answer a text. It is an easy fix or to achieve this. But if you eventually want to enable the model to do, to really output the 3D reconstruction, we probably need to branch the model with another, add another branch to predict the 3D shape or something.
Yeah, but at the very least, we could use it to actually select the images that are could become part of the overall reconstruction, to order them by time and date and so on.
Yeah. I think we can definitely do that because we need to have something.
Okay, thank you.
I mean the relevant one.
Yeah.
Cheers.
So if I might contribute a bit to this discussion, I think Jan used in interest in reconstructing the path through time and space. I think I'm not very sure, but I think that this can be done by leveraging the positional bias, right? Because we know that the depth of the needle in the haystack kind of affects the performance of the model, right? So I think that perhaps if we could do some kind of research around manipulating the depth of the needle in the haystack, it might provide some progress towards reconstructing the path through time and space. So if I know exactly what position each needle occupies within the haystack, it gives me some idea of what time and what specific position this person in the video in the camera feed might have taken during their travels, if that makes sense. I don't know if I explained that well enough.
I think the positional bias issue is about the model show some suboptimal performance on specific when the needle is placed on specific regions. But yeah, and you also mentioned that we can do something like shuffling to fix this issue, or you use this observation.
Not necessarily about shuffling. What I meant by that is we can track the position of the needle, right? By tracking the position of the needles, because you can have single needles, you can have multi needles, right? So if we can track the position of the needles in the haystack, it can make it easier for us to actually reconstruct the path.
Oh yeah.
That's what I mean. Yeah.
Yeah. So given the input, we can definitely directly use that and do some 3D geometry and directly do reconstruction if we know the needle depth.
Yeah. And you're welcome, Janjus. Thank you for being here, and take care. Hope to see you in another of our meetings. Yeah. So does anyone have any other questions? Yeah. Take care, Janjus. Take care. Any other questions? Does anyone have any other questions? Okay, so in the event that you do think of some questions later on, Patrick will provide his contact, and then we can message him our questions. I hope that would not be a problem, Patrick.
What?
I said I hope that would not be a problem. If
Oh,
we could
it's
message
definitely
you with
not.
our
Yeah,
questions.
I'm very welcome if people have any questions after the meeting. Like, please welcome and feel free to ask questions. Like, email me.
Okay.
Yeah.
So thank you very much for being here, Patrick. We appreciate you taking your time to be here
No,
and
definitely. I'm
present
happy
your
to
work
share
to
our
us.
current work. Yeah.
So
Thanks,
thank you very
everyone.
much and take care, everyone.